polynomial. What's the degree of the polynomial on top? 3, right? Degree of the denominator's polynomial? 1, right? So when we say degree, we're looking for the highest power of x. Okay, this one right here, degree of the numerator?
2.
Denominator?
3.
4, 3, 2, 3, yeah, 2, 2. All right, so, but those are all examples of rational functions, right? So our goal is to see if we can integrate these, all right? Find the antiderivatives of these. And I know they look terrible, but we're going to do every single one of those, all right? All right, so let's go back to college algebra and let's talk about partial fractions, or maybe it was the beginning of pre-cal. So what is the strategy? What is our strategy if we want to integrate something like this? Here's the strategy, and I'm going to go through this quickly. The first thing we do is we inspect the degree of the numerator and denominator, just like we did, right? We were just spitting out the numbers. And we have a couple of different scenarios. If the degree of the numerator is less than the degree of the denominator, then we're going to move on to the next step. Okay, so let's go back up here. On the first one, would we just move on to the next step? No, because that's bigger than that, right? How about this one? Will we move on to the next step?
Yes.
Yes. Next step?
No.
No. Next step?
Yes.
Yes, because that's smaller than that. Next step?
No.
No, because that's not smaller than that. Okay, so the first step is to inspect, and if we get a smaller degree on top than the bottom, then we're going to move to the next step. If it's the other way around, if the degree of the numerator is greater than or equal to the denominator, then we first have to do long division. That's the first step. So on this first one, we will be doing long division or no? Yes, we will. Long division? No. Long division? Yes. Long division? Long division? Yes. Okay? Oops, sorry. Let me see if I can silence that here. Shut up. There we go. All right, so inspect, move on, or long division. Okay, after we've done that, we're now step 2. For the remaining rational function, use partial fraction decomposition to rewrite the expression. So this is the stuff from pre-cal. And I could go through this. There's all these different cases, and this just looks terrible. Doesn't that just look terrible? Okay, I think it's better if we just work through examples. Because in mathematics, we have to be very precise about the way we write things, and we have to use a lot of interesting subscripting because why in math do we use subscripting? Do you all know why we use like a sub 1, a sub 2 so much instead of just like a, b, c? Like, do you all know why we subscript in math a lot? Because you don't run out of letters that way. Okay, so like if you had 100 variables, you could call it like x sub 1, x sub 2, x sub 3, x sub 4, and if you're only using 26 letters in an alphabet, then you don't run out of letters. So that's why subscripting is used. But let's just go to the examples. Here we go. So we're going to learn by example here. If you don't recall anything from partial fractions, I think you should take a little time to go try and review. I'll do my best to fill in the holes as we proceed through this. All right, so we look at this. Let's just have some appreciation right now for all the different things we have to take into account here. Right? Is this a basic U sub? Right? Is this integration by parts? Is this trig sub? Is it something we just looked at where it's like, constant over this? So we've really opened up a lot of possibilities here, right? So we look at that for a while. We're like, I don't know. We try some different things maybe. But eventually we get to the point where we're like, look, this is a rational function, right? It's a rational function. The degree of the numerator is bigger than the degree of the denominator. And so I'm going to start by doing long division. Okay, now long division goes like this. You put the numerator in the division box, right? Now, you don't need a plus 0 here, but remember when we do long division, you have to put zeros for any variable that's not represented in the expression. So we have a 1x cubed. We don't have any x squareds, but in long division, you need to create a column for yourself for any x squareds that might appear during the long division process. And then the x is here, and then a column for any constants we have. Does that look familiar?
Yes.
Okay. Now, outside we do the x minus 1. I should also mention that when you do long division, you put these in descending order, highest powers down. All right, so then what we do is we ask ourselves the question, what do I have to multiply x by to create x cubed? That's all you have to look at. So what do you multiply that by? X squared, right? So you can put that anywhere you want up here. I know some instructors tell you like put it on top of the x squared. It doesn't matter where it goes. X squared. Now, you're going to take that x squared, you multiply it here, and then carry those underneath here. So x squared times x is x cubed, and x squared times negative 1 gives you negative x squared, and I'm going to put it right under here, like that. What's the next step? Subtract this, which changes the signs. So I'm going to come in here, and I'm going to change the signs. So that plus becomes minus, that minus becomes a plus. And now we add straight down. So what happens when we add down? Gone here, x squared, here, x, here, nothing. You can put 0 here, or you just leave it like that. And then we play this game again. We say, what do I multiply x by to get x squared? X plus x, okay? And then we just multiply through again. So x times x gives us x squared. X times negative 1 gives us negative x. Come through, subtract, which changes the signs again. So this becomes a minus. This one becomes a plus. And what are we left with this time? Just 2x. So we play this game again. What do we multiply x by to get 2x? 2. So we put 2 here. And multiply. So 2 times x gives us 2x. And then 2 times negative 1 gives us minus 2. Come through. Change the signs. What are we left with this time? 2. And then we play this game again. What do we multiply x by to get 2? We finally got to a point we can't, right? So this is our remainder. This is what's left over. So your next thing is to write R2. Wait, hold on. That's what my daughter does. We're not in that class anymore, right? We're here. There. That's where we are, right? It's your remainder over the divisor. So plus the remainder over the divisor. What this means is this, and I want you all to not lose sight of what we just did here. Like back in grade school, if you do like 15, let's say, divided by 6, right? Then two remainder 3, right? That's old school, right? But what we're saying is that this is equal to 2 plus the remainder over the divisor, right? 2 plus a half. Is that right? 2 plus a half. That's what we're saying. We're saying that 15 over 6 is equal. Oh, I should have reduced this fraction. That's why I was. What goes into both of those? 3? So 5 halves, yeah. So 5 halves is 2 plus a half, right? These are equivalent. They're equivalent expressions. And that's what we're saying here. We're going to replace this expression, right, with this expression. And what would you rather integrate? That or that? That, right? Because you can do them term by term, right? Term by term. So this first one becomes, this integral now turns into the integral of x squared plus x plus 2 plus 2 over x minus 1, all of that dx. And do we feel good about that? Yeah, that we should be able to integrate without much effort, right? 1/3 x cubed plus 1/2 x squared plus 2x plus, drum roll, 2 ln of absolute value of x minus 1 plus c. That one wasn't terrible, was it? I mean, other than the long division, once we got the long division done, the integration wasn't that bad, right? Maybe we should look at another one. Let's look at this. I don't think we're going to go through it. I want everyone to try and figure out, see what you might do with that right now. Does anyone have any ideas on what we might try?
Factor out a 2 from the denominator.
Factor 2 out? Why do you want to do that? I'm just curious.
Oh, so it's the leading term to 1.
For what purpose? For any purpose, or?
You have to factor the denominator.
Okay, so you want to pull out a 2 here to try and factor the denominator? You don't have to do the 2 out. You can't. You have to pull a 2 out if you're going to complete the square. But if you're going to factor, it's not necessary. But why are you factoring? I'm just curious why you want to factor.
To reduce it to parts.
So, like trying to do partial fractions? Okay, everyone remember that partial fraction decomposition, you have to try and factor the denominator. I'm going to go through this more formally next class. I think you want to do that because that's the section we're in, we're talking about it. But let's back up. Maybe we don't need that. Your denominator is cubic, right? Your numerator is quadratic. And we know that when you take a derivative of a cubic, you should get a quadratic, right? Maybe we get lucky and the denominator, the derivative denominator is the numerator. Maybe u is 2x cubed plus 3x squared minus 2x. And what's the derivative of that? Is that what we have up there? Kind of, right? But not really, huh? I could factor a 2 out of here, but that still wouldn't give me that, right? So you remember how earlier I said now I'm going to make the top look like the bottom? That's off the table, and here's why. That works really well when your numerator is linear and your denominator is quadratic. As soon as you go past that and go quadratic over cubic like this, trying to get the numerator to look like the denominator is not going to work for the most part. It's because you can multiply by 1 on the outside, but you can't, that'll let you change the coefficient on this, but the only way to control this coefficient is to multiply by another number, which is going to create your first coefficient to be messed up. So there's just no way you can control them both. So this does not work. I was really hoping, I've given a problem like this on a test, where it's the last question on the test, and it's a basic U sub. And it's like, it's like a 4th degree polynomial here and like a 3rd degree polynomial, and it's just basically u du, and the top is du, and the derivative, or the answer is natural log of the denominator, and that's it. So always be looking for the easiest way out of a problem first, because you don't want to just be like robotic about it and just start doing a 30-minute process for something that you could have knocked out real fast. All right, so yeah, we are stuck at this point. If we say, okay, rational function, right? Degree of the top is 2, degree of the bottom is 3. We do not have to do long division, right? So the question is, what do we do next? And I think that's where we'll start class next time. Sound fair? We will start with, okay, how do we go about doing partial fraction decomposition? So take some time if you can to review it if you haven't seen it in a while. All right, everyone. Have a great day. We'll see you on Thursday. You should be able to start your homework, well, I don't know about your homework for this section. Someone have a book with them? Can I borrow your book, Sully? Let me see what this homework looks like for 6-3. There's not much you can do here for 6-3. So get caught up on everything. Go look at the chapter review and see if you can do any problems out of chapter review if you're caught up on your homework. Let me turn off my camera so we can talk.